So the last general topic on equilibrium we have to talk about is called Lechatlier's principle. The thing to remember about Lechatlier's principle is it's all about systems at equilibrium that are then perturbed. So the big idea here to start with is that you have a system at equilibrium. So in terms of our math, we have an expression for K and not an expression for Q. And then what we do is we apply a change. So if we're at equilibrium and then we apply a change, we are no longer at equilibrium. So then what Lechatlier's principle does, right, is it tells us, okay, how do we get back to equilibrium? And like I said, Lechatlier's principle is essentially a series of rules that we learn, a series of guidelines that help us decide how do we get back to equilibrium. One more time, and I mentioned it just briefly in this little discussion, we start with a system at equilibrium. So we're at a situation where K applies. As soon as you apply a change, now we're no longer at equilibrium, so essentially we're at Q. And then what's going to happen is because you're no longer at equilibrium, the system's going to want to get back to equilibrium. It's going to want to get back to K. So the idea here is that if we understand Q versus K for a lot of the simple cases, then you'll understand how and what's going to happen to the system that gets us back to K. So it's all about Q and K. You're at equilibrium, K is applicable. You apply a change, now you're at Q. How do you get back to K? So the first thing we're going to talk about is simple addition and subtraction of reactants or products. So let's take, for example, the addition or subtraction of product. Now we're going to look at just a really simple like example reaction to kind of see what happens, but then it's going to apply for our more complicated situations. So let's say we have a simple reaction that looks like A going to B. Let's say that we're at equilibrium. So K is going to be B over A in this case. We're at equilibrium. So now let's apply a change. Let's add product. All right, let's add product. So we are at equilibrium. We add in product B. So here's what our expression used to look like. And now B is higher. So if you think about what Q looks like in this situation, well, here was K. And now the numerator has gone up. So if you think about how Q compares to K, well, wait a second, down here we're saying it's higher. So in this situation, Q is greater than K. As soon as you dump product in there, all right, you now have perturbed the equilibrium and Q is bigger than K. Essentially, you dumped product into an equilibrium and now you have too much product, which kind of makes sense. So then we know what happens when Q equals K. We know that the reaction shifts, right, to, I'll draw it up here, the reaction shifts to the reactant side. And that's what happens. When we add product, we make a Q that's greater than K. And how does Lechatlier's principle work? What does it tell us happens? All right, the reaction shifts to make more reactant. All right, pretty simple idea. And again, if we understand Q versus K, then we'll understand a lot of the principles within Lechatlier's principle. So again, just real quick, we add product. The reaction is going to shift to make more product because Q is greater than K at that point. All right. So what'll happen is, right, B will go down, A will go up until you reach K, until your Q becomes K, until you reach equilibrium again. So let's change this up just a second. Let's analyze the same situation. But now let's take product away. Let's remove product. So here's our original K expression. Here's what we would have. But if we take product away, B will go down, right? So we're no longer at K, we're at Q. Well, in this instance, right, if you look here and you look here, well, what's the only difference? There's less B, right? So in this case, Q is less than K. If you somehow figure out a way experimentally to take away B, to take away product, all right, Q is now less than K. Well, what happens when Q is less than K? There's not enough product. Again, this kind of makes sense. If I remove product from equilibrium, there's not enough product there, and so equilibrium is going to shift to make more product. We know when Q is less than K, the product side is favored. So what Lechatlier's principle tells us is that if we take away product, all right, the reaction shifts, or equilibrium shifts, and the wording is the same there. The reaction shifts or the equilibrium shifts to make more product. We take product away, the equilibrium is going to go and try to make more product to make up for that change that we actually enforced. Okay? Now, we can do it real quickly. All right, we can kind of just make the same arguments talking about addition and subtraction of reactant. All right, let me spell that better for you guys. Addition and subtraction of reactant. So if we're doing addition and subtraction of reactant, the exact same ideas apply. You can probably go ahead and fill this in yourself if you wanted to. It's the same sort of idea. Here's a K. What happens if I add reactant? All right. If I add reactant, my expression, which is a Q, now looks like this. If I make the denominator bigger, how does Q compare to K? Well, now it looks like there's too much reactant. The denominator gets bigger and Q gets smaller than K. So in this case, Q is less than K, right? Because the denominator got big. Well, if Q is less than K, what's going to happen? Well, we have too much reactant, so it's going to shift to make more product. And so what Lechatlier's principle tells us is that if you add reactant, then what happens is the equilibrium or the reaction shifts to make more product. Right, the reaction makes more product. Same idea, real quick again. What happens if you subtract reactant? All right. If you subtract reactant, right, then if you look at our Q expression here, so we're at equilibrium, there's a certain B and A. Now we make the denominator go down. And when we make a denominator go down, then we know that our Q expression as it compares to K, right, is going to be bigger than K. We don't have enough reactant at this point. So if we don't have enough reactant, what happens, right? Because Q is greater than K, we have too much product relative to the reactants that we have. We get an equilibrium shift to the left-hand side. We get an equilibrium or reaction shift to make more reactant. So if we subtract reactant, all right, Lechatlier's principle tells us the reaction shifts to make more reactant. Pretty simple idea, being able to be explained with Q and K, all right? But they're nice sort of multiple choice, standard exam type problems to say, hey, here's a reaction set up, here's an equilibrium, what happens if I do this? What happens if I add this, take away that? Just always kind of have this Q versus K stuff in the background, and you'll be set for deciding which way the equilibrium is going to shift to get back to equilibrium, which way the reaction is going to shift to get back to equilibrium. Gets a little bit more hard, but not unbearably so. It's a little bit more difficult when we talk about energy. So this is still underneath Lechatlier's principle. So energy effects. Essentially, one thing that you can do is you can shift equilibrium of a reaction with temperature, right? The K's involved, all right? The K's that we have, our equilibrium constants, they're actually functions of temperature. Right? We'll kind of talk about this more later on in the semester, but K's are function of temperature, okay? So how is equilibrium going to be affected based off of K being a function of temperature? It depends on the sign of delta H, okay? So it's all about delta H, so let's focus on delta H. And we can kind of use the same Q versus K ideas when we focus in on delta H. So if we look at delta H and it's negative, all right, then we know that this is an exothermic process. Now, from the standpoint of thermodynamics and what we learned last semester, when delta H is negative, right, that means that energy is produced. From the standpoint of Lechatlier's principle, if energy is produced, then it's almost like energy is a product. I mean, it's not almost like it is. Energy is a product. Okay. So, all right, we also have a situation, if we're focusing on delta H, so just remember this. If it's exothermic, energy is a product. That's what matters for Lechatlier's principle. What happens when we focus in on delta H and we see that it's positive? We know that that's an endothermic process. Okay, it's an endothermic process. We know that the reaction requires energy. It takes in energy from its surroundings. All right. The reaction requires energy. From the standpoint of Lechatlier's principle, the way that we can view this is it's almost as if energy is a reactant. All right, it's almost like energy is a reactant. So for delta H, that's positive, it's endothermic. Energy is a reactant. That's what we'll remember in the context of Lechatlier's principle. So how does this help? Because what we're going to be doing in the context of Lechatlier's principle is we're going to be cooling reactions, right? Cooling reactions. If we cool reactions, what that means is that the temperature is going down. That means we're removing energy. Right, we're removing energy. So hopefully you can follow the logic here. So now, depending on delta H and whether that energy is acting like a reactant or product, the cooling effect or the heating effect that we're going to talk about in a second is going to have a different effect on the reaction. So for our exothermic situations, right, remember what we said about this? We said that energy was a product. So if we're cooling something and energy is a product, it's like we're removing product. From the last discussion that we just got done doing, right? When you remove product, right, your Q now is less than your K. So you're not really changing concentrations, but you are changing the thermodynamic property of the situation. And like I said, the logic flow here is, all right, I'm removing energy. If energy is a product, I know what happens when I remove product. If I remove product, Q is less than K. We also know from previous work in equilibrium that when Q is less than K, what happens, all right? The reaction shifts, right, to make more products, okay? So Lechatlier's principle says that for exothermic reactions, when we cool them, right, the reaction makes more product. The reaction makes more product. Okay, that kind of makes sense with a Q versus K analysis. It's going to be the same idea when we look at an endothermic reaction that is cooled. If I look at an endothermic reaction and I lower the temperature cooling that reaction, I'm removing energy. But remember, for endothermic reactions, the energy acts like a reactant. right? Energy acts like a reactant. All right, well, from our previous analysis for work we've already done, what happens if you remove a reactant? Well, the reactants are in the denominator. So if I make the denominator smaller, Q becomes greater than K, right? So we know what happens in this situation, right? We know in this situation, we don't have enough reactants. We have too many products, and the reaction shifts to the reactant side. One more time, removing energy for an endothermic process where situations exist where energy is acting like a reactant means that we don't have enough reactant at that instance. We've removed reactant, Q has risen above K, and so you'll see an equilibrium shift to the left-hand side. The equilibrium will shift to make more reactants to deal with this change. Okay. One more time with the same logic in terms of energy effects. What happens when we heat a reaction? Well, it depends on whether it's an endothermic or an exothermic process. If we heat a reaction, that means we're raising the temperature. All right, in terms of energy, it's like we're adding energy to the system. All right, so then let's look at the two cases we have. Now, unlike cooling it, right, it's the opposite. We're putting more energy in. So let's look at a situation where delta H is negative first. Let's do an exothermic situation. Remember, for exothermic situations, the energy is a product. Okay, energy is a product. We are adding energy to the system. Hopefully you guys can predict what I'm going to write here. Okay, we're adding product here. Q is greater than K. All right, adding energy to the system with energy being a product raises your Q because the products are in the numerator. All right, so we know when Q is greater than K and we have reactants here and products here. It means essentially we don't have enough reactants. We have too many products. The reaction shifts to make more reactants. It shifts to the reactant side, right? We have too many products. We put too much energy into the situation. Again, same logic ideas, right, that we had before. What happens when we have an endothermic delta H, a delta H that's positive, and energy is a reactant, and we heat it, and we're adding energy to the system? Well, hold on a second, all right? Energy is a reactant. I'm putting more reactant into the situation, into the system. Where are the reactants in Q? They're in the denominator. So I'm making the denominator bigger, and in this instance, Q is less than K. So what happens to the equilibrium in terms of a shift? Well, when Q is less than K, we know that the equilibrium shifts to make more products, all right? So if I have a situation where I see that it's endothermic, all right, it requires energy. So guess what? If I give it more energy, it's going to make more product, okay? So a lot of the things with Lechatlier's principle can be explained with a Q versus K analysis. So if you're comfortable doing those, and you should be by now, then you're going to be comfortable with actually a Lechatlier's principle analysis. Where things get a little bit tricky is we have to talk about special consideration with gases. Because when we're talking about gases, all right, we have situations where we're dealing with pressures. Now, we do know that pressures are related to concentrations. But the thing about Lechatlier's principle, right, is that we're going to try to view this from the standpoint of Lechatlier's principle tries to deal with the stress that you put on the situation, right? For gases, it's all about alleviating stress. right? And so there are just some things to know, okay? So before I get to what the actual principle statements are, what Lechatlier's principle means for gases, here are the things that we're going to be doing, right? We're going to have some gases in a container, and we're going to be compressing the container. And we're going to make those gases and the reaction of gases exist in a smaller space. When we decrease the volume, right? When the volume gets smaller, see how the square is smaller? When the volume gets smaller, we call that compression. We should know this from last semester, right? We could also go in the opposite direction. Okay, with our reaction, we could also make it go into a bigger area, bigger volume. And when we put a gas in a bigger volume or a reaction in a bigger volume, we call that an expansion. Right? Now, actually, compressions and expansions will change the behavior of gas because if you look up here, right, you're going to get K and Q differences occurring because volume plays a role in pressure and concentration, okay? And we can really only do this with gases. They're the only thing that are compressible, so we don't have to worry about these situations for liquids or solids or aqueous situations. These are only special considerations for gases because this volume shows up as playing a role in P's, all right, which will be involved in KP's, or concentrations, which would be involved in KC's. So we can see from here, all right, compression and expansion will definitely change our equilibrium situations. It'll change our thermodynamics. So then here are the rules. All right. It's all about keeping the number of gas particles as consistent as possible, all right? So this is the general rule of thumb. It's all about alleviating stress, all right? Try to keep the number of gas particles as consistent as possible. All right. Try to keep the number of gas particles as consistent as possible. And like I said, I'll try to explain it as we get into what the rules are. So here are the things that we're going to do to a system of gases, to a reaction involving gases. We're going to compress the system. And here's our rule for Lechatlier's principle, the way that we alleviate the stress, the way that we keep the number of gas particles as consistent as possible, is that when we compress a reaction, right, when we make it exist in a smaller volume, right, the equilibrium shifts to the side of the reaction with less moles of gas. You literally look at the stoichiometric coefficient. If you think about it, the gas particles are existing in a smaller volume. So we actually want to decrease those number of particles so we can kind of stay consistent with the concentrations and pressures that we saw before, all right? So if we compress the system, equilibrium shifts to the side of the reaction with less moles of gas. Notice it's a little bit different than our other rules. It's not shifts the reactant, it shifts to the products. You actually have to look at the reaction and decide, where do I see smaller stoichiometric coefficients? Where do I see less moles of gas? That's the side that's going to be favored when you compress something, right? It's opposite for expansions. When we talk about expanding a gas, all right, we have a container, there's a reaction going on, we move the actual walls of the container, we make it a bigger volume for the gas to live in, right? Now it looks like we don't have as much gas per unit volume. We want those pressures, those moles of particles to be as consistent as possible for a given volume. So when we expand the gas, right, equilibrium shifts to the side of the reaction with more moles of gas, right? With more moles of gas. So again, we have a certain situation. There's a certain amount of moles of particles per that volume. As you make the volume bigger, the reaction is going to want to make more gas particles. So it finds which side has bigger stoichiometric coefficients, and it shifts that way. Okay, so quick little example for the last 2 points, because it is a little bit different. It's not as easy as a K versus Q. Let's just do 2H2 gas plus O2 gas in equilibrium with 2H2O gas. Now, if I'm going to talk about making a change to the system in terms of compression and expansion, what I have to look at is the number of moles of gas, all right? On this side, and I just look at gas, you don't look at solid or liquids or anything like that, all right? I see that I have 3, all right, stoichiometric coefficient, 3 moles of gas on this side. On this side, I have 2. So right away, then we can apply our Lechatlier's principle ideas. And we're going to say, okay, what if I have this set up at equilibrium and then I compress the system, right? What's going to happen, right? When you compress the system, the side with less, all right, moles of gas are going to be favored or is favored. So when I compress the system, you're going to make more H2O gas. You're going to make more product. So that's an important idea to know, though, like from an engineering standpoint. What if I wanted to run this reaction? Well, I could set it up. I could bring it to equilibrium. If I want to maximize the amount of this that I make, I'm going to go ahead and compress it. For this reaction, if we expand the container holding these gases and we do an expansion, right? We know that for an expansion, the side with more moles of gas is favored. So if I have this set up and at equilibrium, but I expand the container, I make it bigger, then actually what you're going to get is more reactant. You're going to get more H2 gas and more O2 gas, right? Because equilibrium is going to shift based off of those Lechatlier's principle statements we just looked at, okay? Again, where I'm getting these numbers from are from the stoichiometric coefficients. And again, I'm only looking at gases to apply situations where we compress and expand, right? One last quick little special consideration with gases, right? Our gases are ideal. And so what happens if we add an inert, and for some reason this gets asked a lot, what happens if we add an inert, non-reacting gas into our gaseous reaction mixture, okay? Essentially what Lechatlier's principle says to us is nothing happens. And again, this goes back to the idea that for this semester, all our gases are going to be ideal. So if I look at a container and I think about these blue gas particles that are in a reaction with these green gas particles, right? And the blue and the green, they're in some sort of equilibrium with each other. Now, I know based off our discussion today that if I somehow change these concentrations, if I somehow change these pressures, then I'm going to get a perturbation to this equilibrium, and Lechatlier's principle is going to tell me that something changes. Remember the idea of ideal gases, though, is that these guys never really see each other. They never feel each other. The volume of this green guy is this big blue square. That's the same volume of this blue guy in this blue square, because these guys themselves are assumed to not take up any volume themselves, which is an assumption that's only valid under certain situations. So what happens if I throw in some red gas? All right, and the red gas isn't going to be involved in the reaction. That's what inert means. It's not going to change the concentrations of these through a reactant. We use the same ideal gas approximation for the red gas. So does the red gas itself take up any space? Well, no. So then has this green gas, does it feel anything differently? All right, does it exist in the same, right, container? Does it exist in the same volume? We're not compressing, we're not expanding. Sure it does. It exists in the same volume, so nothing happens. There's nothing that actually changes the equilibrium when I put an inert, non-reacting gas in there. So Lechatlier principle is all these ideas just encapsulated into like one section. What you do is you look for what's applicable for a given problem? Am I talking about gases and expanding or contracting them? Am I talking about gases and throwing in another inert gas? Am I looking at the energetics of a system? I'm looking at cooling or heating something, and I'm looking for an effect on equilibrium. Am I adding or subtracting reactant or product, right? These are all the considerations that you have, but it doesn't get more complicated than this. So if you understand this and you wrote good notes and you send me good questions, then this is all you'll need to actually get to understand Lechatlier's principle.